Okay, can you guys see lecture notes? Good. So, how was your week so far? And this week flies by so fast. I feel like I'm just getting started. I'm like, we just started. It's already Wednesday. God, I've got to figure out what the hell I'm going to be doing next week. So, stressing out a lot. It keeps it interesting. Life doesn't get boring. No, it doesn't work that way. We got to keep you guys going. We got goals. Okay. Okay. So you guys are familiar with the different phases, right? So we're going to be talking about phase transitions. Okay. And we're going to talk about it. I'm going to give you guys some examples, and then we're going to try to work some of the problems. Okay. So today's lab is primarily working some of those problems. Okay, so phase transitions, when we sit there and we think about the different phases, there are three major phases that we talk about: solid, liquid, gas, and I can't remember, solid, liquid, and gas. Okay, now there's also another phase called plasma, right? And we'll be talking about that in this class, okay? So when we go from one phase to the other, that's called phase transition. Okay, so if I go from a solid to a liquid, that's a phase transition. That phase transition has a name that's associated with it, right? Let me go check on them. Okay, I got there like 5 minutes before the class to start, and I knocked on the door, and nobody answered, and I waited out there for like another, I'm not gonna lie, like another minute, and then I was like, okay, I'm going home. I left. I didn't even try to go to the library. I was like, no. But it wasn't open like at all. So I was like, I'm guessing the guy didn't come in and set up the room. Yeah. Did you go? No, I didn't. No, yeah. Really? Yeah, exactly. I found it. Wow. Well, I have a micro bin. Mid-March, yeah, exactly. Well, I go to mostly the our campus, and it doesn't matter class yet. So I had business in the morning, and today was my last day, so I had it. So it was supposed to be 1:50, but I got out earlier, and then I go home, take a nap, and I come back again. Didn't want to stay.
Nothing was bad. Everything's okay. So does anybody know where someone is? Okay. Why can't I see you guys? Anyone there? Are you guys there? Marcel?
I exist.
Yeah.
Okay, good. Okay, I just want to make sure it's not showing up for some reason. Not everything is showing up on my screen. Okay, so we're talking about transitions. So if we go from solid to liquid, it's called what? Solid to a liquid. It's melting, right? Okay, so we know that it's melting, right? And so you guys can kind of see that in this little, in our little diagram right here, right? Melting. Okay. Let's see. I have to figure out which one to look at. Melting, right? So we know that that's melting. Okay. Now, if we go from a liquid to gas, that's either evaporation or vaporization. Okay. Now, if I go from a liquid to a solid, freezing. If I go from a gas to a liquid, condensation. Right? Now, there are points where we can go directly from a gas to a solid. Okay, if we go from a gas to a solid, it's called deposition. If we go from a solid to a gas, it's called sublimation. Okay, so dry ice sublimes at room temperature, right? Okay, occasionally you'll see the term fusion. Fusion is the same thing as melting. Okay. Now, these processes are dynamic, right? Meaning that they're going to be happening. And they're going to reach a state, you can get a state of equilibrium where you're able to go in both directions, right? So the thing that we want to keep in mind is that we reach a dynamic equilibrium, which basically means that the rate of going from one transition to the other, and then going from the other, from one phase to the other, and going back to that phase, that rate is going to be the same. Okay. So the rate for water to freeze and for water to melt is going to be the same. Yes, exactly. It's not going to be one's faster, one's slower. It's going to be the same. The rate is going to be the same. See, they worry me a little bit too much. They're having a little too much fun over there. Let's see. Okay, so are you guys with me so far? Okay. Okay, so things that we're going to want to take in consideration is going to be vapor pressure. And vapor pressure is going to be influenced by the intermolecular forces. Do you guys remember intermolecular forces? I was going to throw something at you. Like, oh, it's going to be one of those days. It's already started. Okay, so the weaker the intermolecular forces, such as like in the case of hydrocarbons, basically organic compounds that don't have OHs or anything like that, just have hydrogen and carbons, those guys are going to have just dispersionary forces, dispersion forces, right? Where things that have hydrogen bonds, right? Those guys are going to have, well, let me see. Those that have hydrocarbons are going to have a weaker vapor pressure or a lower vapor pressure. I'm sorry. Okay, let me take that back. Hydrocarbons are going to have a higher vapor pressure because you have only the dispersion forces. You have weaker forces. Okay, So let me correct myself. The things like water that hydrogen bonds that have dipole-dipole, those guys are going to have lower vapor pressure, right? Because you're going to have them connecting more with each other. Okay, so the vapor pressure, that's right. So the stronger the intermolecular forces, the lower the vapor pressure, or the weaker the vapor pressure. Okay. Okay. So, like, for instance, if we take a look at the vapor pressure above a lake, right? So the vapor pressure above a lake reaches a state of equilibrium, right? So you have some of it that's going up into vapor, and then some of it that's actually going back down into water. So it's gonna, that rate of it going up and the rate that it's going down is gonna be equal. Long as we don't mess with the temperature or anything like that, we kind of keep that stuff constant, we're okay, right? So, but if there's a really hot day, what's gonna happen? The water is going to vaporize. It's going to change it. And then it's going to have to try to reestablish that equilibrium, right? So the rate is still going to be the same, but it has to reestablish it. Does that make sense? For that particular temperature that we're raising it up to. Okay. Okay, so if that's the case, the number of molecules that are going into that gas phase is going to be the same. It's not going to change over time. Okay, because it's going to be in equilibrium. So they should cancel each other out. The ones that are going up, the ones that are going down, they should be canceling each other out. Okay. So the vapor pressure over a liquid is going to basically remain constant. Okay, so we're going to basically have a constant value for vapor pressure. Okay, and then again, this is going to be influenced by that intermolecular forces. Okay, so here's an example. If you guys take a look at the in figure A, so the liquid is going to be escaping into the vapor, right? And then at the same rate, the vapor is going to be coming back into the liquid. Okay. And so if you take a look in a closed container, once equilibrium is going to be reached, the value of that vapor pressure is going to be exactly the same once it's reached. Okay. And if you kind of take a look at it at equilibrium, this last one basically shows it, that vapor pressure is going to be exactly the same. Okay. Okay, so now I want you guys to think about this. Here are 4 different compounds. We have ethanol, we have ethylene glycol, and we have diethyl ether and water. Okay, 4 different compounds. Okay, now in terms of their vapor pressure, which would we expect to have the highest vapor pressure and which one would we expect to have the lowest vapor pressure? Okay, because of what? Okay, so you're saying water would have the lowest out of all 4? Okay, so it technically can make 2 hydrogen bonds, right? In that case, okay? So then that would have the lowest vapor pressure. So you're right. The ethylene glycol will have the lowest vapor pressure, right? And again, because it has more forces that are involved and stronger forces that are going to be involved. Then it would be water. Then it would be ethanol or ethyl ether, diethyl ether. It does, right? But again, we're talking about hydrocarbons. And do we have a hydrogen bond anywhere over here? We do. Is this a guy gonna form a hydrogen bond, this oxygen, all by itself? Yeah. So technically it can form two hydrogen bonds, right? Yes, that's the reason why it would be above ethanol. Because both of those hydrogens are gonna form hydrogen bonds, or can form. Where this guy only has one that can form. And this one has two independent, right? So that one is going to be, it's going to have the lowest vapor pressure, but it's going to have the strongest IMS, right? Okay. Piece of cake? Okay, so so if our vapor pressure on a liquid is going to increase, it's going to increase with temperature, right? And we kind of talked about that earlier, right? So we kind of know that the rate of that equilibrium is going to also go faster as we increase temperature. And we can kind of determine that by let's say lakes that are in very warm places. They get really low in the summer, right? Or rivers or little, okay? So like here, you see how dry the river is, right? At one point that river was running, right? I mean, of course they cut off the flow of it, but it actually, as the temperature gets hotter, it'll get lower, right? And more shallower. So, and then that just basically means that those vapor pressures are going up. So vapor pressure is going to be dependent on temperature. Okay. Okay, and this just basically shows you that. So you're going to increase the number of molecules at low temperature, right? You're going to have more molecules that are going to be in the liquid more component. But as we increase the temperature, we're going to have more kinetics, right? Okay. And so that means that you're going to have a lot of them being released. Okay. So as temperature increases at high temperature, the kinetic energy is going to be higher. At low temperature, the kinetic energy is going to be lower. And that makes sense. We know that, right? Okay. So boiling points. So when the vapor pressure of a liquid increases enough to be equal to the external pressure, external atmospheric pressure, then we reached our boiling point. Okay. So when vapor pressure equals our atmospheric pressure, then we've reached boiling point. Yes, sir. Okay. Yeah. It will, it's kind of stuck. Like mine.
So okay, I was gonna wait some time, and by the time that we like sort of went, you, yeah, I had a stack like this.
Okay, so sorry about that. I forgot what we were talking about. Okay, so when the vapor pressure and the atmospheric pressure are equal, that's when we reach our boil. Okay, so things start to boil at that point. Okay, so we know that vapor pressure is going to be dependent on temperature, right? And we also know that that's also going to affect when things start to boil, right? Because your more temperature you put into it is going to affect this thing. Okay. Okay. So normal boiling point of a liquid is going to be defined as the temperature when the vapor pressure equals 1 atmosphere. Okay. Because we know that is atmospheric pressure. Okay. So if we go to a higher altitude, let's say we go up to the mountains, right? How's that going to affect our boiling point? Okay, why?
What I'm trying to get, what I'm trying to get from this is that the higher we go is going to be lower because we're opposite to each other, right? Pretty much.
Okay, so the higher atmosphere, what happens at higher atmosphere? What is the pressure like at higher atmosphere? You're going to have less pressure, right? So if we have less pressure, right? So less atmospheric pressure. Yeah, right. That, yeah. So if we have less atmospheric pressure, then it's going to take less time to boil, right? So we're going to reach our boiling point, or a lower temperature to boil. We're going to reach our boiling point is going to be lower. So it's going to reach faster, but it's going to be a lower boiling point. Yes, because less atmosphere. Yeah. Yeah. So at sea level is atmospheric pressure is about 1 atm. Okay. As we go up higher, the pressure gets lower. Atmospheric pressure gets lower. Okay. Make sense? And so that's why you get lightheaded, less pressure, less. Okay. Okay. Atmospheric pressure gets lower at higher altitudes. So if you're baking a cake, right, are you going to bake it? And let's say we bake it both at 350 degrees Celsius. Or Fahrenheit, sorry. Yes, 350 degrees Fahrenheit. My bad. Sorry. My head is in 50 different places right now. So. Okay, so Fahrenheit, 350 degrees Fahrenheit. It would burn if we're in higher altitude. Yes. We would be burning cakes daily if we just followed the instructions, right? Okay, does that make sense? Kind of good? Okay, so increasing the external pressure increases the boiling point. Decreasing the external pressure decreases the boiling point. Did I say that right? Okay, increase, decrease. Okay, yeah. That is correct. So the more pressure you have, yes.
Wait, let me write it down and I'll show you.
Sure. She says, and at the microscopic level. So let's say we're increasing that external pressure, right? So, and then she was talking about the collision of molecules. Pressure, you're going to have more collisions that are going to occur. Yeah. Okay, so the heat of vaporization. The heat of vaporization is basically defined as the amount of heat that is required to convert 1 mole of liquid to gas. Okay, now you will have, we'll make reference to the heat of vaporization, the heat of vaporization, or the heat of transition, right? So I'll say that very generally, the heat of transition is always going to be converting from one phase to the other. You have to get over that hump. There has to be so much energy to make it over that hump. If you don't have enough energy to make it over that hump, you may be at the temperature, but you won't go from, let's say, liquid to ice. Kinda, yes. So like a threshold, you have to get over a threshold, right? Exactly. So if you don't reach a certain energy threshold, then you won't go into the next phase. So in other words, if you have water, water will remain water. And you'll see this in some cases where water remains water and it doesn't go to ice, even though it's at 0 degrees Celsius. Yes, that's right. Yes, exactly. Yeah. And so there has to be an energy threshold that needs to be reached. And that is represented by the enthalpy. Okay, does that make sense? Okay, so I'm going to show you a diagram. I'm going to handwrite a diagram. So bear with me. Okay. Okay. Okay, this here represents temperature. This here is going to represent those phase transitions, right? So here, this here represents, this is something that is ice, so this is below 0. As we get to 0, this here represents that change in enthalpy, delta H. So do you guys remember heat capacity, right? Your specific heat capacity, right? So this is the specific heat capacity. This is for a heat capacity for going to ice. So delta C cat, delta, M cat. It's been a while. M cat ice. This here is M cat liquid. This here is going to be delta H vaporization. Delta H V. This is going to be delta H fusion. Okay. So it's the energy that is associated to get over the hump to go from ice to water. Okay. And that's what you're seeing here. So if you're calculating the energy associated to go from below 0 to, let's say, 120 degrees, right? Which is clearly going to be a vapor, right? This would be MCAT, sorry. MCAT gas or vapor. So MV delta T. MCAT V delta T. Okay. The energy is going to be the sum of all of those phases added together. So our change in energy is going to equal, let me see if I can, it's going to equal M cat ice delta T plus delta H of fusion plus M cat liquid L delta plus delta H. And I shouldn't say MCAT liquid. I should tell you mass times the specific heat of ice times the change in temperature plus MCAT vapor, or sorry, M heat capacity of vapor, the change in temperature, delta T. Okay. So if we're going from below freezing to a high temperature, it's going to be the sum of all of those parts. Okay. Good. So let's move on. Oh yeah, sorry. I was just checking the time. And often your change in enthalpy, it really should be, because enthalpy is really, it's kilograms per mole, right? So you'd have to multiply it by the number of moles of water you have. So technically it should be N to be more specific. So it should be N meaning the number of moles in both of these situations. Yeah. So now sometimes they just give you the energy. They're assuming that it's 1 mole. Okay. How you doing? Okay, good. Okay, how did he go? You got a burrito? Good. That's good. No, he didn't. At least he might have. Hold on. No. Is he okay? He's where? Oh, his car? Okay. 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 No, I didn't know. Okay, so if we think about the boiling points, we've talked about the vapor pressure. Tell me about the boiling points of these three, of these 4 different compounds: ethanol, ethylene glycol, diethyl ether, and water. So we would expect what? Who would have the highest boiling point? What was that? Ethylene glycol would have the highest boiling point. Who would have the next highest boiling point? Water. And then it would be alcohol, and then it would be diethyl ether. And that's basically what you guys are seeing here, right? Now, this here represents the pressure, right? So this represents that external pressure, right? So as that external pressure changes, that means that the boiling temperature is going to change, right? So boiling point is just the temperature where we boil, okay? So at 1 atmosphere, which is how many pascals? Or kilopascals? It's 101 exactly. Good. Yes. Yes, it is 101.325, right? You guys remember that? Okay, so that's exactly where this line is drawn at. So that's basically atmospheric pressure. That's where we're at down here, particularly in cooling, we're at atmospheric pressure. In Fireball, right, the pressure is going to be there a little bit higher in elevation, just a little bit, not too much, right? So, but that means that the pressure is going to be lower Or is it going to be a little bit higher? It's lower. That's right. Okay. So when we look at the effects, remember guys, when you guys did the Mentos experiment, right? If we look at the effects of the Mentos experiment, and if we had enough samples to compare Ulinga to Fireball, which we never do, right? And we could get it on a really nice hot day where the temperatures are exactly the same, which will never happen for some reason, right? We would expect what to happen with the soda. Would it go higher in Fireball or higher in Ulinga? And why? So it has less pressure pushing down, so then it should actually go up higher, right? Make sense? So in theory, if the temperatures are always exactly the same, Fireball should have a higher squirt than Ulinga does, right? Okay, so we know that pressure, right? That vapor pressure is going to be dependent on temperature, right? So let me show you how. So this is the Clausius-Clapeyron equation. The Clausius-Clapeyron equation basically allows us to figure out how to calculate our vapor pressure, right? So the natural log of pressure is going to be equal to the enthalpy of vaporization divided by RT. R is the ideal gas constant. In this unit, in this case, R is going to be 8.31 joules per moles Kelvin. Okay. And you're going to ask me why, right? So don't worry about it. I'll give it to you in a minute. Okay. And temperature has to be done in Kelvin. Okay. Okay. And then plus A represents a constant. Okay. So if we're comparing two pressures at two different temperatures, let's say we're changing our pressure. We're changing our temperature. In one case, we know that we can calculate the pressure at that new temperature if we have the delta H. Okay. Okay. So in that case, we can change our equation. If we actually plug in it for the two different temperatures, we end up with ln2 divided by, ln P2 divided by P1 equals delta H vape divided by R, and then that's all multiplied by 1 divided by T1 minus 1 divided by T2. Okay? Yeah, look. So it's just an equation that you guys are gonna kind of have to memorize. Right? With a little bit of calculus, I could actually show you how to get there. Right? And it's actually an integral equation to get us there. But you guys will learn that more in physical chemistry. I'll save it for you. Okay, so you want to try to memorize this equation, keep it in the back of your head, and when we're trying to figure out the vapor pressures, okay? And the change of vapor pressures depending on temperature. Right? We know it's dependent on temperature. Okay, so the heat of vaporization is going to be the same. Okay, so here, this here represents the heat of sublimation, right? Sublimation, again, is going from what to what? It's going from a solid to a gas. That is correct. So the heat of sublimation is going to be equal to the sum of the heat of fusion and the heat of vaporization. Basically, the heat resulting from melting to a gas, right? And that makes sense, right? Yeah, no, maybe. Right? Because if we're going from sublimation is going from a solid to a gas, right? And we talked about the whole concept of equilibrium, right? So if I'm going from a gas, so solid to a gas, right? Solid to a gas. So if I'm going from a solid to a liquid, then I'm going from a liquid to a gas. That should equal the same as just going straight there. Okay. I'm saying that they're equal to each other, right? So this guy is going from, let's say, here's my solid to my little gas balls, right? That's what we're doing. That's what sublimation is, right? But that's the same thing as going from a solid to a liquid, my liquid, okay, to a gas, okay? So the energy that it takes to get to that hump and the energy that it takes to get to that hump has to equal the energy that it takes to get to the full thing. Yeah. Okay. Good. Okay. Okay. So we already talked about this. I got ahead of myself. You know. So here, this is just basically showing you again the temperature, right? And this is the amount of heat or the heat that's going to be associated with going up, or the amount of energy, right? Okay. And so this here is going to be, and Q, remember heat represents mass times C delta T. This is that equation that we just wrote, literally. Okay. Okay, let's see if you guys got it. Calculate the total amount of energy required to convert 135 grams of water from negative 15 degrees Celsius to 120 degrees Celsius. The calculations, the heat calculation for temperature change is Q equals C delta T. The heat calculation for state change is Q equals N delta H. The specific heat capacity of water in the solid state is 2.09 joules per degree Celsius grams. Liquid state, 4.184 joules per degree Celsius grams, and 1.84 joules per degree Celsius grams in the gas state. The heat of fusion for water is 6.01 kilojoules per mole, and the heat of vaporization is 44.01 kilojoules per mole. Okay, do you guys want to start it together? You got time to kind of work it through? Okay, so, sorry, Jan didn't get enough sleep last night. So let's go back to our little figure here. It kind of helps us with this process. Okay, so in this case, we're starting at negative 15 degrees, right? So we're going from negative 15 degrees to 0 degrees. Okay, so then our Q ice is going to equal our mass, which is 135, times, which is in grams, our specific heat of the ice, which is 2.9, 2.09, sorry, 2.09. Oops. And that's joules, grams Celsius. And we're subtracting, we're going from negative 15, which would be our initial temperature. So it's our T final minus our T initial, right? And that's going to be our delta. Okay, so then that would be a positive 15 degrees. Okay, so if we do the math, what did you guys get for that? Okay, I get 40,500. Okay, hold on. 15 times 2.09 times 135. Oh, wait a minute. Hold on, I get something entirely different. Hold on. 15 times 135 times 2.09. Sorry, I get something entirely different. Let me try this again. 15 times 2.09 times 135. Okay, I get 4,232.25, right? Okay, so it's 3 sig figs. So then we get 4,000. I was just testing you. $4,230. And that units would be joules, right? Okay. Okay, so then we also have the delta H, right? So we have delta H fusion. Delta H fusion times the number of moles. Okay, what are the number of moles? How do I calculate the number of moles? The mass divided by the molar mass. What is the molar mass of water? Say it. 18. Okay, so we divide 135 by 18, right? Right? Don't tell me you forgot that already, right? So we know that N is going to be 7.5. So we're going to put this over here just for our benefit. N equals 7.5 moles. And if we're being exact, it should be 7.50 moles. 3 sig figs, right? Okay, so our delta H of fusion is what? I believe it's 6.01. Okay. Okay, so we multiply our number of moles. It's going to be 7.50 moles times our delta H of fusion, which is 6.01, and that is, well, it's actually kilojoules. So we should probably put it in joules, right? 6.01 times 10 to the third joules. So we can keep the same units per mole. Uh, 135 divided by 18. Check it to be sure, because I'm on a roll today. So I'm just putting stuff in. Yes, you want to cancel out the grams, right? So if we have 135, so then you divide it by 18 grams, right? Per mole. Yeah. Yeah. So you divide it by. So 135 divided by 18. Okay. My calculator is doing crazy stuff today. Okay, so then we end up with 7.5 times 6.01. 4.51 times 10 to the fourth power, and that's joules. Okay, so now we're going from 0 to 100, because that's where water is going to be at, right? 0 to 100. So we want to use Q water is going to equal 135 grams times the specific heat of water, 4.184. You know, that's joules per grams Celsius times the change in temperature. So our initial and our final. So that would be 100 minus 0. So it's just 100. So multiply it by 100. And that's going to equal some number. Times 4.8, 4 times 100. So that's, now correct me if I'm wrong, because so far I've been wrong by everything. 56, 3 sig figs we're looking at, because actually it was 100.0. 56 point, I mean 56,400 or 500. And I'm running out of room, joules. Okay. Okay. So now we need the delta H vaporization. So again, that's going to be N delta HV. So that's going to equal 7.50 times the heat of fusion is, heat of vaporization is it 44, is that kilojoules or is it 44? Okay, so then it's 4.4 01 times 10 to the 4th joules per mole. And you guys know I'm just converting from kilojoules to joules by multiplying by 1,000. Come on. So I get 3.3 times 10 to the 10 to the 5 joules. Okay. And then we're going up that last stage from 100 to 120, right? So that's 20 degrees, right? 100 minus 120, 120 minus 100, 20 degrees. So we'll use that Q again times 135 grams times the specific heat capacity of a vapor, which is liquid, solid, gas, 1.84, and that's joules per degree Celsius and grams, right? Okay. And then we'll apply that by the change in temperature, which is 20 degrees Celsius. Okay. I'll work on my third grade handwriting. Times 135 times 20. So I get 4,968. So if we go sig fig, so that's 4,970 joules. Okay, so then I add it all together, each one. So the sum is going to equal plus 3.3 EE to the 5th plus 56,500 plus 4.51 4.51 0.51 EE. Oh crap. So, plus 3.3 EE to the fifth plus 56 500 plus 4.51 EE. Ah, my phone is screwing up. So 4 plus 3.3 EE to the fifth plus 56 500 plus 4.51 EE to the fourth plus 4,230 equals 440,800. And if we do sig figs, and that's joules, sig figs wise, it should be 4.40 in scientific notation times 10 to the fifth joules. So what you guys got? More or less? Okay. So, yes. Mm-hmm. Oh, 4.41. Oh, yeah, you're right, actually. It should be 4.41. Right. I just ignored my 8. 4.41. Yes, you're right. So it would be 3 sig figs for that. Okay. Good question. Okay, so pretty intense question, pretty long, right? Okay, I think we are at our time point for this class, for the lecture. Okay, so for the lab, we can start talking about that. We've gone over most of the questions. Well, we've gone over a lot of the calculations. There's just a little bit more. So what we'll do is we'll finish the other questions that we didn't cover when I give her the rest of that lecture on Monday. Yes, Monday. Okay, so for your lab today, it's problems. It's just these problems. So you guys should be able to do, oh, actually, I want to go over one more thing if you guys don't mind. It'll take me 5 minutes. Maybe a little bit more. Okay, the last thing that I want to go over is phase diagrams today. So phase diagrams it's just where we're comparing temperature and pressure, and we're getting a visual of the phase transitions. Okay, I said a phase diagram is where we're comparing temperature and pressure, and we're getting a visual of the phase transitions, right? Because we know that it's going to change as your pressure and temperature changes. Okay, so let me show you an example. This is an example of a phase diagram. Okay, so here we're going from solid to liquid to gas. This here is called the triple point. This is where we can go straight from a gas to a liquid. So if you take a look at, straight from a solid to a gas. Below the triple point, we're going through sublimation, right? So you're going from a solid state to a gas state. Here, this is where your freezing and melting is at. This here is where your vaporization and condensation is at. Here, this is where our sublimation, and deposition. So below the triple point is where you have all three states. Okay, you have a solid, you have liquid, and you have gas present in all three states. This here is called the critical point. The critical point is the point where the liquid and the gas state, there's no clear distinction. And that's kind of where your plasma is going to end up being. Okay. Okay, so if we take a look at this, although there's no numbers here, right? Usually they have numbers that are going to be associated with the pressure scale, and there's going to be numbers associated with the temperature scale. So the way that you would read this is that you would go over to the line, and that would be temperature that you would have that phase transition at that particular pressure. Okay, so minus 10 degrees Celsius and 50 degrees kilopascals. These are kilopascals. This is Celsius. Okay, so what phase would we be in? For A, sorry, minus 10 degrees Celsius and 50. Okay, so minus 10 degrees Celsius. So 10 degrees Celsius is going to be 0. So somewhere like here, right? And then at 50 kilopascals. Oh, sorry, minus 10. I'm a hot mess. I'm like, that's not working. Minus 10. I was looking at 10. I'm like, no. Okay, minus 10, 50 right here. So we're a solid, right? Okay. It's been a long day. 25 degrees Celsius and 90 kilopascals. Okay, so liquid. That's probably not 25. That's probably more like 20, right? Okay. So what is the next? 50 degrees Celsius and 40 kilopascals. So 50. I guess that is probably more 50 degrees right here. I'm a little, okay, 50 degrees Celsius, and you said 40 pascals, which is going to be about right here ish. What do you guys think? Solid, liquid, or gas? Liquid. Okay. And let me clear. It's just all looking like a hot mess right now. 80 degrees Celsius, 5 degrees kilopascals. Okay, so water vapor. Okay. So somewhere over here. And minus 10 degrees Celsius, 0.3 kilopascals. So solid? Yep. So I'd say solid too. So it's right here, over. It's about minus 10, so somewhere in there. Okay, and minus 50 and 0.3. Okay. We have the gas. Okay, what about 0.6 kilopascals and 0.01? So what say would it be? All of them. Yeah. Piece of cake? Yeah, the scale is crazy. Okay. Okay, so that should allow you guys to do all the way up to 6. And then we'll finish 7, 8, 9, 10. I mean 7, 8, 9, and 10 on Monday before we do our other lab. Okay. Okay, piece of cake. Yeah. Didn't I already? I did. Yes. Good. Okay. I will. I'll be posting your other lab so you guys can look at it, but I'll hand it out on Monday. And what I'll try to do is give you both labs on Monday. So. Yes. You need one as well? There, I have more over there. Just put that one with. I'll go grab it. It's in the classroom. In the classroom. So on my desk. It should be in the classroom on my desk. If it's not, let me know and I'll go get it from the office. You did get it. Jesse didn't get it though. He wasn't here. Yeah. So you can give that to Jesse. Okay. Okay. Any questions? Concerns? Cash? So you guys can sit around and do it, or you guys can go home and do it. If you have any questions, we can talk about it on Monday. Yeah, you can go home. It's that first week I'm giving you guys a little, or second week, it's a little bit lax, you know. Actually, that's hella early too, huh? I should probably screw that. 50, so let's see. So the question was, it was 50 degrees Celsius and 40. Oh, okay, 15.3. So it's 0.3 and 50. Oh, you're right. I should have been over. So I should be gas. I'm screwing it up a little bit there. Okay. So on Monday, we'll talk more about supercritical fluids and we'll talk about the lattices and stuff. Lattices. Lattices. Yeah.
He's like, he actually
Lattices. Bye. Have a good day.